Picture this, right? You buy a brand new phone. It's got a brilliant screen, an amazing camera, and, the biggest selling point of all, a truly personalized, on-device AI assistant.
Oh, yeah. The ultimate digital companion.
Exactly. This AI is supposed to be your second brain. It's going to read your emails, look at your photos, remember your favorite restaurants. But then, like 6 months later, the phone just starts running incredibly hot.
Right, and the battery is draining in, what, 2 hours?
Yeah. And when you ask it something simple like, hey, what was the name of that book my sister recommended last summer? It just freezes, panics, and tells you it has no idea.
Well, I mean, it is the classic technological bottleneck we are hitting right now. We expect our everyday devices to maintain this perfect, pixel-perfect vault of our entire lives, and we just expect the AI to understand all of it simultaneously.
So welcome to the deep dive. Our mission today is figuring out how we can actually give personal AI assistants a human-like, lifelong memory on everyday edge devices, like that smartphone in your pocket.
And doing it without instantly melting the processor or maxing out your storage.
Exactly. So to figure this out, we're looking at a stack of generative AI architecture papers today. But the absolute star of the show is this fascinating May 2026 paper by Jiali Chang and Yuxiang Ren. It's titled ScrapMem, a bio-inspired framework for on-device personalized agent memory via optical forgetting.
It's such a great paper because it fundamentally rethinks how a machine should remember things. I mean, for a long time, the industry just assumed that better AI memory meant bigger hard drives and faster chips.
Right, just throwing more hardware at it.
Yeah, exactly. But this paper suggests we need to look in a completely different direction.
And if you are listening to this, I know you want the insight into where this cutting-edge tech is heading, but you definitely don't want to spend your entire afternoon decoding matrix algebra.
Definitely not.
So consider this deep dive your shortcut to being well-informed. Okay, let's unpack this. Why is it so incredibly hard to just give an AI a giant hard drive of our lives? Like, why can't my phone's AI just remember everything I do?
Well, it really comes down to the brutal constraints of what we call edge devices. Unlike a massive server farm in the cloud, your phone or your smartwatch has strict physical limits on memory, battery life, and compute power.
Right, it's a tiny box.
Exactly. And to have a truly personalized agent, it needs to process multimodal data because, your life isn't just a clean, perfectly formatted spreadsheet of text.
I'm not even close.
Yeah.
My digital life is like a total chaotic mess of dog photos, blurry screenshots of recipes, random calendar invites, messy voice notes.
Which is exactly the problem. Current AI memory paradigms fail spectacularly when they try to handle that specific messy mix on a small device. Let's look at the two main ways engineers have tried to solve this so far.
Okay, what's the first one?
The first approach is called parametric memory. Imagine trying to teach an AI about your life by permanently rewiring its brain. You basically bake the knowledge directly into the model's weights using fine-tuning techniques.
Okay, so it's like trying to train a puppy. You just do the repetition over and over until the behavior is, just part of who the puppy is.
That's actually a really good way to picture it. But parametric memory suffers from a huge issue, a phenomenon called catastrophic forgetting.
Catastrophic forgetting. That sounds bad.
It is. If you tweak the model's brain today so it remembers you adopted a dog, well, the mathematical adjustments might accidentally scramble what it learned last month about your peanut allergy.
Oh, wow. So you fix one memory and accidentally delete another one.
Right. Furthermore, it completely lacks interpretability. If the AI gets a fact wrong, you can't just open a file to fix it. The memory is just this massive soup of numbers distributed across a neural network.
So baking the memories directly into the AI's brain is way too risky and messy. What about the other route? Like, why not just give the AI a superpowered search engine to look through my files?
Well, that brings us to the second paradigm, which is retrieval augmented generation, often called RAG. This is where the AI takes all your files and converts them into high-dimensional semantic vectors.
Okay, vectors.
Yeah, think of vectors as translating complex ideas into GPS coordinates on a massive map of concepts.
Okay, got it. So a picture of my dog and the text word puppy end up with similar GPS coordinates on this map.
Precisely. But RG struggles massively when you start mixing different types of media. Comparing the vector coordinates of a really text-heavy email with the coordinates of a silent video clip is computationally super awkward.
I can imagine. It's like comparing apples and, airplanes.
Right. And beyond that, as you generate years of this multimodal data, just retrieving it isn't enough. When you ask a question, the system has to pull all those relevant files and actively feed them into the AI's context window.
The context window, that's like the working memory, right? The amount of stuff the AI can hold in its head at one single time, well, it formulates an answer for you.
Yes. And that context window gets overwhelmed almost instantly on a smartphone.
So it's basically like trying to cram an entire storage unit of mismatched boxes like photo albums, tax returns, old home movies, random sticky notes into a tiny studio apartment.
A perfect analogy.
Right, and the apartment is my phone's processor, and the boxes are my data. So if I ask the AI to find my tax returns, it tries to drag 30 boxes into the room all at once. Eventually, you can't find anything. The AI gets totally overwhelmed trying to look at it all, and you literally have no space to even walk.
Exactly. The traditional methods are essentially just trying to buy a slightly bigger studio apartment or forcefully cramming more boxes through the front door. Neither of those works long term.
But ScrapMem fixes this.
Yeah, ScrapMem takes a totally different approach. The researchers realized that if the storage unit method doesn't work for machines, they needed to look at the only system we know of that successfully manages decades of complex, multimodal memories without running out of space.
Human biology. Because, I mean, I don't have a solid-state drive in my head, but I somehow remember my childhood home, the smell of rain, and how to ride a bike. So how does ScrapMem actually borrow from biology?
It grounds itself in a concept from cognitive neuroscience called the complementary learning systems theory, or CLS. Basically, in the human brain, memory relies on a cooperative dynamic between two distinct areas, the hippocampus and the neocortex.
I always hear those biological terms thrown around, but let's actually define them in the context of memory. What does the hippocampus do?
Think of the hippocampus as your fast learner. It rapidly binds visual scenes, emotions, and contextual cues together into episodic memories. It's what allows for one-shot learning.
Like when you touch a hot stove.
Yes, exactly. You touch a hot stove, you see the red coil, you feel the burn. Your hippocampus binds all those different sensory modalities instantly, but those initial bindings are somewhat fragile.
So they fade if they aren't backed up somewhere.
Right. Over time, the neocortex takes over. The neocortex is the slow learner. It gradually consolidates those transient, fast-bound experiences into structured, stable, long-term knowledge.
Okay, I like that. Fast binding of scenes by the hippocampus, followed by the slow consolidation of the actual underlying knowledge by the neocortex. So how does the ScrapMem paper translate this biological dynamic into AI?
They translate it into a literal scrapbook for the AI. The scrapbook approach is brilliant in its simplicity. Instead of storing your photos in one database, your texts in a vector store, and your app usage history somewhere else.
It puts them together.
Yes. ScrapMem aggregates everything from a specific period of time, say a single afternoon, and literally pastes them onto a single temporal image representation, a scrapbook page.
Wait, really? A literal image file?
Yeah. Your texts, your photos, your behavioral traces, all unified visually into one single image file.
Okay, wait, hold on. I need to poke a hole in this because my brain is flashing a massive red error message right now. Usually pictures take up way more space on my hard drive than a simple text document.
That is the common assumption, yes.
Right, like if I type out a grocery list, it's just a few kilobytes of data. If I take a high-resolution photo of that exact same grocery list, it's several megabytes. How on earth is turning all my lightweight text into a giant heavy image, safe space for an AI running on my phone?
Well, what's fascinating here is the critical distinction between raw pixel storage on your hard drive and AI token consumption in the processor.
Token consumption. Walk me through that. I've heard the word, but how does it work?
Okay, so when a large language model reads text, it doesn't read like you or I do. It breaks words down into tokens, which you can think of as chunks of computational effort.
So reading takes effort.
Exactly. A long, winding history of your text messages over a month might require tens of thousands of tokens for the AI to process. Reading those tokens eats up a massive amount of your phone's computational memory and completely hogs that context window we talked about earlier.
Oh, I see. Okay, so text is cheap to save on the hard drive, but it's incredibly exhausting for the AI to actually read when it's actively thinking about a problem.
That is the crux of it. And here is the mind-blowing finding the paper leverages from recent research into vision language models, specifically citing DeepSeek OCR. Rendering that dense multimodal content as a single visual image actually compresses the token consumption by nearly a factor of 10 compared to feeding it raw text.
Wait, a factor of 10? That's huge.
It is. Vision language models have become extraordinarily efficient. Visual tokens are incredibly dense with information. When you lay out your texts, maps, and photos visually on a scrapbook page, the AI doesn't read it line by line sequentially.
You just looked at the whole thing at once.
Yes. It looks at the whole layout simultaneously. It can extract the meaning, the spatial relationships, and the context using just a fraction of the computational effort it would take to read everything serially as text. It leverages the high information density of human vision.
So, it's like the difference between me reading a 10-page, highly detailed architectural description of a house versus just looking at a blueprint for 5 seconds. The blueprint might technically be a larger file size on a computer hard drive, but my brain understands the layout instantly. Looking at a scrapbook page is 10 times easier for the AI's brain than reading a giant spreadsheet of my daily data.
A perfect parallel. It is a massive leap in on-device efficiency.
Okay, I am totally sold on the token economy. We've pasted our lives into an image-based scrapbook to save all this processing power and battery life. But, I mean, a scrapbook is basically useless if I have to flip through 400 pages manually just to find out when I last went to the doctor.
Right, you still need to be able to search it.
Yeah, how does the AI actually read this visual diary out to answer a specific question quickly?
That brings us to the retrieval mechanism. ScrapMem builds an index using what they call an optical perception pipeline. This pipeline acts as the bridge between the raw images and actionable knowledge.
So it's basically looking at the pages and taking notes. How does the pipeline actually work?
Well, it employs a vision encoder. In their testing, they utilized a model called Qwen3VL2B Instruct, running alongside optical character recognition, or OCR.
Okay.
When the pipeline looks at a newly minted scrapbook page, it extracts two distinct things to create a hybrid node set. First, it pulls out visual nodes. These are just the raw visual features of a photo. Second, it uses a language model to read the text on the page and extract semantic nodes, the underlying meaning, the entities involved, the actual events.
Got it. So it's essentially pulling out the key puzzle pieces from the image and separating them into things it saw and facts it read.
And then comes the crucial step. It organizes these scattered puzzle pieces into an EM graph, which stands for episodic memory graph. It arranges related nodes into EM paths, which are basically logical, causal, or temporal chains of events.
Okay, I think I need a concrete example of an EM path. How does it link a picture and a fact together?
The paper provides a great medical scenario for this. Imagine a scrapbook page generated from last Tuesday. The optical perception pipeline scans it and extracts a visual node. Let's say it's a photo of a person lying on a hospital bed.
Okay, that's the visual node.
Right. And it simultaneously extracts a text node from an OCR doctor's note pasted next to it on the page. And that text note says, visited hospital due to fever.
Got it. Visual node is the hospital bed, text node is the fever.
Exactly. And then the EM graph's job is to connect these into a logical progression. The path it creates goes from diagnosis, influenza, to treatment, medication, and rest. That entire interconnected path is now an indexed memory.
Ah, I see. So it's not just randomly scanning the scrapbook until it spots the word flu. I'm picturing like a detective's corkboard. You know the ones in the movies with the red string connecting all the clues?
Yes, a classic trope, but very, very accurate here.
The visual nodes and the text nodes are basically the Polaroids and the sticky notes physically pinned to the board. And the EM graph is the red string connecting the picture of the hospital bed to the sticky note about the flu medicine. It builds all the context.
The red string analogy is spot on. And to trace that red string when you actually ask a question, ScrapMem uses a Q matrix.
A Q matrix?
Yeah, the paper refers to it mathematically as a binary incidence matrix, but practically speaking, think of it as a custom-cut stencil. When you ask, when did I have the flu, the system lays the stencil over your massive corkboard.
Oh, that's cool.
Right. The stencil blocks out all the irrelevant noise and perfectly highlights only the red string leading to the hospital bed, the date, and the medication. It completely bypasses the need to reread everything.
Okay, but does this actually hold up if you have years of this data? Because theory is great, but a lifetime of memories is a lot of red string to sort through. The paper mentions something called a joint at 10 score of 51.0%. What does that actually mean in plain English?
Well, they tested ScrapMem on the ATM Bench dataset, which essentially simulates 4 years of real-world personal data, emails, images, browsing history, all of it.
That's a lot of data for a phone.
Definitely. And the joint at 10 metric essentially tests if the AI can retrieve the perfect combination of related facts out of that massive pile. Hitting 51% means that more than half the time, it perfectly navigates 4 years of complex, interconnected memories to find the exact 10 pieces of context needed.
Wow.
For fragmented, multimodal data, that is an incredibly high benchmark. But where ScrapMem truly separated itself from the pack was in a category called list recall.
List recall, so like finding a bunch of scattered items.
Exactly. Imagine asking your AI, what are all the different coffee shops I visited on my business trip to Seattle over 5 days?
Okay, yeah.
Traditional text-based RH systems stumble here because the mentions of coffee shops are buried in dozens of separate disconnected text files or location pings. But because ScrapMem aggregates everything into a visual layout on a daily scrapbook page, it captures the spatial and temporal context of your day much better.
Oh, I see.
It hit over 50% accuracy on list recall, while the next best traditional method was stuck way down in the 30s.
That makes total sense. It's looking at the spatial relationship of your whole day as one snapshot, rather than trying to, hunt for the word coffee across 500 separate text files.
Exactly. The visual layout inherently preserves the narrative of the day.
But here's the elephant in the room for me. 4 years of data, even optimized into visual scrapbook pages and indexed with the detective's red string, is still going to get really heavy eventually. My phone only has so much storage.
That is the ultimate challenge.
Right. To truly survive on a device for a lifetime, an AI needs to deal with the reality that we generate gigabytes of new data every single month. And this is where the paper introduces a concept that I think is completely revolutionary. For the AI to remember the important stuff long term, it has to learn how to do something uniquely human.
It has to learn how to forget.
Yes, the magic of optical forgetting. How does an AI actively forget something without just, hitting the delete button?
It routes right back to that biological inspiration we talked about. Human memories naturally fade. We lose the granular, hyper-specific details over time, but we retain the core narrative.
Sure, I don't remember what I ate for lunch 3 years ago, but I remember the vacation I was on.
Exactly. ScrapMem models this temporal degradation by dynamically reducing the resolution of older scrapbook pages. As a memory crosses specific age thresholds, say 180 days old or maybe 2 years old, the system literally blurs the digital page.
It physically blurs it.
Yes, it lowers the JPEG quality, increases compression artifacts, and shrinks the scaling factor.
So a memory from 2 years ago literally looks blurrier to the AI than a memory from yesterday afternoon.
The fine, trivial visual details fade away, but the broad visual strokes and the large text, the core structure of the memory, they remain intact.
But hold on, let's poke a hole on this too. If the AI already extracted the text and built the corkboard with all the red strings, why not just delete the picture entirely once it's indexed?
It's a common question, actually.
Like, why keep a blurry JPEG at all? Doesn't that still take up precious space?
It's a great question. You keep the blurred image because life isn't perfectly categorized. Sometimes, a year down the line, you ask a question that the AI didn't anticipate when it first built the corkboard.
Right. You surprise it.
Exactly. By keeping the blurred visual, the AI retains a spatial and contextual gist, like a backup map. It remembers where things were on the page and the general color palettes or layouts, which can help trigger related nodes without the heavy storage cost of a crystal clear image. It acts as a safety net for fuzzy queries.
That is fascinating. It basically keeps the vibe of the memory. But does blurring it actually save a meaningful amount of space?
Oh, the efficiency gains are staggering. In their testing, they utilized a configuration called the timed gentle setting. By progressively degrading the visual fidelity of memories as they aged, the total storage footprint plummeted from a raw 4,302 megabytes down to just 299.5 megabytes.
Wait, I want to make sure I heard that right. 4,300 megabytes down to 300.
Yes, a massive 93% reduction in storage space.
But surely that breaks the system, right? If you intentionally make the AI's vision blurry and force it to forget the details, if I ask it a specific question about a trip from 3 years ago, and the page is just a pixelated mess, won't it just guess and hallucinate a response?
Well, if we connect this to the bigger picture of the EM graph we discussed, the data proves otherwise. Even under their most aggressive forgetting setting called Boundary 365, where memories degrade very quickly, the system retains over 90% of its peak reasoning performance.
How is that even possible? How can it look at a blurry page and still get the answer right 90% of the time?
Because the semantic backbone survives. The system relies on the red strings on the corkboard, combined with the macro-level structures that survive the blur. The optical forgetting is functioning as a powerful form of cognitive filtering.
Cognitive filtering. So just dumping the noise to save the signal.
Exactly. It discards the redundant, time-decay details that the AI doesn't actually need to answer high-level questions about your life while keeping the main story intact.
That makes sense.
Think about your own memory. You probably don't remember the exact pattern of the wallpaper in that hospital room from a few years ago, or what color shirt the doctor was wearing, but you definitely remember the flu diagnosis and the medication. ScrapMem mimics that perfectly. It drops the wallpaper, keeps the diagnosis.
So what does this all mean?
It means we finally have a viable blueprint for deploying true, lifelong, personalized AI on edge devices. By treating data not as a sterile, permanent database, but as a biological scrapbook that naturally ages and fades, we decouple memory performance from storage limits.
That's incredible.
Yeah, we can have a privacy-preserving AI living entirely on our phones, learning about us over decades, without destroying the hardware.
It's just such a huge shift in perspective. To get an AI that fits in our pocket and truly understands us, we had to stop treating memory like a hard drive and start treating it like a human brain.
Exactly right.
We paste the texts and images together into a temporal scrapbook to save computational tokens. We connect the events with a red string episodic graph so it can find things instantly. And most importantly, we allow the unimportant details to literally physically blur out over time to save space.
The deliberate mechanism of forgetting turns out to be just as important as the mechanism of remembering.
Which actually brings me to a final thought I want to leave you with today, looking at the implications of a system like this. If our devices are going to use optical forgetting to literally blur out the trivial details of our past to save space, who or what algorithm decides what counts as a trivial detail?
That is the lingering question behind all personalized tech, isn't it?
It really is. If our AI assistant gradually becomes our external lifelong memory, and it systematically fades out the messy, minor visual quirks of our past based on some mathematical definition of efficiency, will we eventually lose access to those seemingly unimportant human memories too, simply because our AI didn't deem them semantically salient enough to keep in focus? It's something to ponder the next time you ask your phone to remember a moment for you.
Very well said.
We want to thank you so much for joining us on this deep dive into ScrapMem and the biological future of AI memory. Keep questioning the tech around you, and we will catch you on the next one.